this computer. Very good. So, hello, anyone. I apologize for my poor English, but I do my best. I don't try to improve with time, but I should. Now Roshin is there to correct me if I'm making big mistakes. And today we have the third seminar of the MPG series, which means that there are online seminars in English on topics that you can propose. We have that every 2 or 3 months, depending on the proposal. And today I come to something that I discussed previously, which is the formalism for describing dispersed system. Indeed, it's more physics than chemistry, except that if we want to organize system, we need some chemistry to arrange the molecule together. So there will be a strange mix. It's physics story told by a chemist. So now I share the page. How do I do that? I don't know. Sharing here, share, okay. Full screen, probably there is a full screen somewhere. No, here it is. Okay, share, and you should see a beautiful village from Alsace. Do you see it?
Yes.
Okay, very good. So now I can display the PowerPoint, and please tell me if you see it correctly. Is it okay now?
Yes, sir.
Yes.
Very good. Okay. So indeed, for years, since 2001, I improved formalism, which is like an algebra, but it's not exactly an algebra, or it is the equivalent of the formalism that is used by chemists to explain chemical reactions. This formalism is based on the chemistry formalism. At the beginning, the name was CDS, Complex Dispersed Formalism. Then it moved to NPOS, Non-Periodical Organization of Space. And finally, it was DSF, Dispersed System Formalism. But since last year, I'm changing everything because I realized that there were bad properties of the formalism. The formalism was all right, except that it was not a good educational object, in particular because it was not following the big idea that we should first, the most important first, and then the detail. And the formalism had to change in this regard. It changed in another regard, which is that we have to, I mean, it's better to move from the simplest to the more complex. So this is the story. And now what I want to do today is to go into details to explain how to use it. It's very simple, but one needs to see it once. And then when you apply it, it is very, very powerful. So this is the story that we are going to see. So it starts from the question, what is food? So food is something that we eat. I make a big difference between food and nutrients, or food with food ingredients. And indeed, molecular and physical gastronomy is studying the transformation between ingredients and food. So finally, I should not say food, but probably dishes. So this is one dish, and this dish is organized. So it is organized here at the macroscopic level. We see from top to bottom a layer of sauce, a white bowl, a yellow bowl, a layer of herbs, and a layer of sauce. Of course, we can. I'm not discussing the detail. I'm just saying the main story because I don't want to be lost in details. What I know is that if I'm using a microscope to look at any part, I will see a different picture. for example, this is the sauce. So you see the sauce is an emulsion with oil droplets dispersed into water or into an aqueous solution. When physical chemists say oil, it means melted fat of any kind. It has to be liquid. And when we see water, it means aqueous phase. So liquid aqueous phase. So I will use these words, oil, water, very simple. On this particular picture, you see three air bubbles, the small circles with black surrounding. So they are air droplets, but indeed they are just artifacts. There are no air bubbles into mayonnaise. This is an emulsion. It is not a very thick emulsion. It is a fluid emulsion because the oil droplets are not close enough to make it very viscous. So, but I come back to the story. We started from the macroscopic organization. We took one part, looking at microscope, and we see a microscopic organization. In this particular one, the organization is random. But indeed, we see something that we can describe. And finally, if we look at any part of this microscopic organization, we would be able to see a nanoscopic organization or mesoscopic. Mesoscopic is probably a better word than nanoscopic because nanoscopic has two drawbacks. First, it has to be nano, and then, you know, for emulsion, there is a confusion between nano emulsion and micro emulsion. So I'm using mesoscopic, but it is not the end of the story. Finally, you go deeper to supramolecular organization. So we will not go even deeper to atomic organization into molecules, but we stop here. So we have 4 levels. And when I was describing any level, I have to give one word of this particular picture. There are raspberries on the left, and I added some tin SN2 plus ions, and suddenly it turned purple because of the complexation of the tin ions over the anthocyanin. So indeed, there is a supramolecular organization. Supramolecular means that it is not covalent. It has to be, for example, van der Waals, hydrophobic, hydrogen bonds, even disulfide, but disulfide bridges are generally considered covalent. So you see, there are different forces to keep the molecular entities together. Up to now, I use a lot of words, and with words, it's very long. And this is why the formalism has been introduced in mathematics first by Claude Viette or Descartes, René Descartes, and others. And indeed, it's very short and very efficient because you write down some symbols and you have the same idea that with a lot of words, and you can reduce the words in order to think more efficiently. In this particular extract, which is an extract from a treatise of logic by Goblet, it's in French, but I'm translating. There are 2 sentences that I want to insist on. Notation or formalism can lead to discovery. This is the first point. This is why in the title of the talk I said for the NDSF for description and innovation. And the reason why we can get some new system is because if you have some symbols and you arrange them automatically into new chains of symbols, you have new chains of symbols which correspond to physical objects. So this idea is based on the formalism of chemistry. This is the paragraph where Lavoisier, the founding father of modern chemistry, introduced the language of chemistry. He said, I built some kind of formulas that could be confused with algebraic formulas, but don't follow the same principle. But indeed, it's again a formalism. So now let's come back to the NDSF formalism. It is very simple. So you see, all the letters or symbols that you will use are there. So we have, I'm starting from the bottom right, phases. So liquid, gas, water, and solid. So very simple. If you have a picture of a system, and if you see a liquid, you write either W if it is an aqueous solution, or O if it is oil. Okay. Gas is gas, an air bubble is gas, and the solids are solids. For example, if you put sand into your mayonnaise, you would have sand crystals dispersed into the emulsion. The dimensions now, bottom left, the dimensions are very simple as well. Let's keep it simple. Imagine that you have a plate in front of you. The dimension of the plate is about 20 centimeters. Okay. Now, if you have something that has the same size of the plate, for example, a big piece of salmon or a steak or something like this, it is a D3 object. It's an object of dimension 3, which means that the size of the object is the same order of magnitude as the size of the plate. So very simple. Now, imagine that you put a sheet of lettuce, for example. Now it is dimension 2, as we are used to that in mathematics. And for lines, the spaghetti would be dimension 1, and a rice seed would be dimension 0. So it's very simple. So this is a description. For example, I use the example of the level of the plate. But now, if you are moving down at the level of what you see on the microscope, it's exactly the same story. Under the microscope, you will see objects of dimension 3, dimension 2, dimension 1, and dimension 0. So now you see that at any level, macroscopic, microscopic, mesoscopic, and supramolecular, we have objects of dimension 3, 2, 1, and 0. Of course, this means as well that when you want to make a description, you have to fix first the level. There will be different formulas for different levels of the same object. Now, the objects are not randomly organized. Sometimes they are. For example, in the mayonnaise or the emulsions that we have seen, the oil objects are randomly dispersed. So we have the anti-slash symbol. I have to explain why the anti-slash symbol. Because in food chemistry and food physics, when you have an emulsion, it is written generally O/W. Or W/O, not anti-slash. And I consider that it is a mistake. It is an historical mistake, because when you look at an emulsion, the main of the emulsion is a continuous phase, which is water for the mayonnaise. And then you disperse the oil droplets. So you have to, I know because I taught the NDSF formalism for years, in particular at master level. I know that the students are annoyed to see the secondary phase before the first one. And this is why there is a proposal, and mayonnaise is first water, W, and then inside water, you have a random dispersion of oil droplets, so anti-slash O. So you see, very simple. Sometimes you can have two phases dispersed into one. For example, imagine that you take an egg white, which is water. Indeed, it's 10% protein dissolved into water. And imagine that you whip. In the beginning, you will add air bubbles. So you see, you have W, anti-slash, and G for gas. Now imagine that you are adding oil to this system while whipping. Indeed, you will have still the water phase W, anti-slash because you have a dispersion of something into it. And what do you have? You have oil and gas. So O plus G. Now, inclusion. Inclusion is very simple. When you include something into something, you have an inclusion. So the mathematical symbol exists. Formerly, it was an arrobas because in chemistry, for inclusion complexes, the arrobas was used, but it is not a good solution because the use of the arrobas was not entirely decided by UPAC, and inclusion speaks to anyone. Superposition, I don't take time to explain. If you put something over something, you have a superposition. And X, I will have to explain later on example. But indeed, when you have two continuous faces and they are intermeshed or intermixed or intricated, I don't know the right word in English, probably intermeshed, because I've seen that in scientific papers, then you use the X. So let's look at some systems now. For example, this is chocolate. The physical state of chocolate depends of its temperature because at -10, everything is solid, all fat is solid, the sugar is solid, the plant material is solid. But if you move to more than 40 degrees, the chocolate is melting. And then you see that the state of chocolate, the physical state of chocolate depends on temperature. Here, what you see under the microscope are fat crystals from chocolate, and inside you have some liquid fat. So you see, this is a good example of two continuous phases. There is certainly a solid continuous phase of fat crystals, but inside the fat that melts easier is melted and it is a liquid. And the demonstration that you have the two systems is that when you push some mercury, which is a technical method called mercury porosimetry, you blow out the liquid fat. So you see the liquid fat makes a continuum network, and this continuum network is intermeshed with the solid network. So clearly here, you would have a formula with S for solid, X for intermeshing, and O for oil. So this is very simple. And now there is only one question that remains. Should you write SXO or OSX? And this has to be considered later. On the cream of espresso, it's a foam. So a foam is very simple. You have water first, and then anti-slash and gas because you have air bubbles. So W anti-slash G. And indeed, I have to add that for all what I'm saying, I'm using the international definition from UPAC. A foam is not an emulsion. An emulsion is not a foam. What is a gel? Everything is given in UPAC. So if you need, go to UPAC Gold Book, very simple, online for free. And you see a dispersion in which a large proportion of gas, nobody knows what is large. And this is a question because, for example, in the emulsions that I showed you before, what we see first is the water phase. What we see then is the oil droplets. But I told you that there were 3 air bubbles. Should we consider them? And my answer is no, because it is more than 1 order of magnitude less than the number of oil droplets, for example. And we can have another definition. Okay, so let's move to plant tissue. Plant tissues are gels because according to the definition of UPAC, this is a microscopic picture of shallot, okay? So we see the cells. Inside the cells, it's mostly water. And the definition of gels by UPAC is non-fluid colloidal network or polymer network that is expanded throughout its whole volume by the fluid. This is exactly what we see. Okay, so this is a gel, okay? Now, with the potatoes under the microscope, we have the same story, except that we have now the starch granules, they are colored in blue, dispersed into the liquid, and all this is dispersed into the solid. So let's let's begin by the most important. It is the solid. Potato is a solid. Now, we see that some cells, which is water, let's say, is dispersed into the solid. So we have S anti-slash because it's a random dispersion, W, okay? But not a simple W because we have the solid starch granule. So we have W anti-slash S. And we have, for this complex system, we have only 3 letters plus 3 operators. So very simple. Egg yolks are made of granules, small solids dispersed in a plasma. Of course, again, on this picture, you see an air bubble, that it's an artifact. And when you describe this system, you should not consider the air bubble. So you have solid dispersed into a liquid, so water, because it's water, mainly anti-slash S. Okay. Another advantage of using the anti-slash and putting the continuous phase first is that very frequently, when we discuss food, we forget the water, which is the most important. For example, meat is 70% water, lettuce plant tissue is 99%. So water is first, and it is an intellectual mistake to consider the details before the main story, I would say. Now, imagine that you make a custard, you add some sugar crystals, and now we have a question very frequently by the students, because on the previous picture, we said that we have starch granules dispersed into water. Okay, it's right. And now, this is not what we see, because at this level, we see the sugar crystals dispersed into the egg yolk. And then, at this level, it's probably to say that the continuous phase is a liquid, which is a liquid. So let's say mainly water, so water, W, anti-slash, and S for the sugar crystals. Again, some air droplets. And when you just mix the sugar with the egg yolk to make a custard or to make a genoise or something, you don't see many air bubbles, but when you whip, now the pastry chefs know very well that when you whip egg white plus sugar, it turns white. But why does it turn white? They don't know, but indeed, what we are making is not an egg white, but a yolk white. And it becomes very, very white if you whip for a very long time. At the same time, you see that the sugar crystals are dissolving, but you have a lot of air bubbles. By the way, I take advantage of this picture to tell you that during the weekend, I make a lot of experiments whipping egg white and egg yolk together to make omelette, to make soufflé, to make genoise. And it is said that egg yolk into egg white prevents foaming, but it's not true. You get a large amount of foaming. And if you are interested, there is even a paper from last year in which it was demonstrated that the proteins from egg yolk make more bigger and more stable foam than the protein from the egg white. I know that it sounds paradoxical, but it is a fact that they have been measured. Now, this is a foam. So for this particular picture, how should we which formula should we find? So let's begin simply. It's a continuous phase of water, W. Then there is a random dispersion, anti-slash. And what do we find? Air bubbles, G, plus some solids, sugar crystal, S. So you see, finally, W, anti-slash, and between parentheses, S plus G. When you make a custard, you see the granules coagulate, and we have the same picture as before, the same formula as before. Now we move to the question of gels, because gels are most important in cooking, because we eat mostly gel. Meat is a gel, fish is a gel, carrot is a gel, asparagus is a gel, jelly is a gel, of course, jam is a gel, and so on. So the sauces are not gels, but the meat and fish and vegetables and fruits are gel. Okay, so the question is, there are many different gels. So this is one for plant tissues. This is another one for meat. So you see, meat are fibers, muscular fibers, so dimension one, obviously, that are aligned together to make bundles. So they are aligned. There is an organization in the bundles, but the bundle itself is dimension one. And inside it, you have a random dispersion anti-slash of the dimension one objects. And this makes meat. Okay. You see now the formula of this one is not the same as the one for the plant tissue. Now for jelly, here it is, for jelly or gelatin gels, what you have, the proteins are making a continuous network. So it's D3, D3 because it's three-dimensional. And inside, the water is making, again, another D3 continuous network. And the two are intermeshed. So we have D3 water, X D3 solid, or D3 solid, X D3 water. So now I have to decide, should we write down D3 solid X D3 water, or W, sorry, or should we write D3W anti-slash D3S? After some research, it appears that we need to organize in terms of increasing complexity, and a solid is less complex than a liquid, because in the liquid, the molecules move at random. In the solid, they are fixed one against the other. So the entropy is much more into a liquid than into a solid. And this can give you the order. So the order would be solid first, then liquid, then gas. And among liquids, the order would be certainly water before oil, because for water, you have hydrogen bonds plus the van der Waals forces, that, and for the oil, you have only the van der Waals forces. And now I come back to the story. We have many different gels. The egg white, the coagulated egg white, is a gel of the same kind. And I leave you as an exercise, if I may say, the question to find the formula of the cooked egg white and the cooked egg yolk. I have to add that this picture of an egg white is an awful picture, because you see a dark color around the yolk, and this means that the proteins have been destroyed by heat, as you can show using a paper that has been put into a solution of lead acetate, which is colorless. And when you put this paper over an egg that cooked, it turns black because of H2S reaction with lead acetate and precipitation of lead sulfur or sulfide. I don't know how to say it in English, but this is another story. So don't eat such eggs, but we have to come back to gel. Now, we have seen many gels. We want to understand the relationship between the formula and their properties. So this is a gel, gelatin gel, or two gelatin gels, 20% gelatin on the left, 5% on the right. And after the gel has been made, I put some methylene blue on top, and you see that the diffusion of methylene blue into the water that is making the water phase into the gel, the diffusion is occurring at different velocities. And that anyway, after some time, it will turn blue everywhere because there is some diffusion of methylene blue molecules into water. This was not the case for the shallot, for example. And indeed, we have very different systems, very different gels, and we need to give them different names because it would be cumbersome to say diffusive gels or non-diffusive gels. So you see, non-diffusive gels, 6 syllables, it becomes to be very long. When I was a student, I was taught with this table. The teacher told us that you can disperse a gas or a liquid and a solid into a gas or into the liquid into a solid, and some names are given. Okay, why not? But this works only for the most simple system. And indeed, when you have the potato, remember, the names that you have seen don't apply. And we need something more. And this is why the formalism was introduced. So I go fast. So remember, we have to decide for a scale. Imagine that we decide for describing the potato at this level, at this scale. Okay. Now, I told you many times, we have to use a big idea, which is we have to move in decreasing orders of magnitude. So the most important first. So here I'm using, in order to explain this idea, I'm using a nuclear magnetic resonance spectrum. Okay. So when you have a spectrum like this, what you see is one signal at 4.7 ppm. This is very simple. Indeed, it is the signal of water into a coffee. So coffee, if you have a cup of coffee, it's a very complex chemical system, but indeed, it's not complex because it is mostly water. When you have analyzed that, this question, water, that when you know that the coffee is made of water, now you can move to the second order of magnitude. It means that you multiply the spectrum by 10, for example. And then we see 1, 2, 3, 4, 5 signals. So it's very simple indeed, because generally in NMR, nuclear magnetic resonance, when you have a molecule, an organic molecule has more than one kind of hydrogen atoms. And each kind of hydrogen atoms create a signal. So with 5 signals, it means probably that the most important molecules after water and coffee are 1 or 2 molecules only. So very simple. And then you multiply by 10 and by 10, and finally, finally you reach the level of the noise, and you stop because the method can you tell more. So this is exactly what we are going to do with food. Here, we define first a dimension. We say that the dimension will be between 10 to the minus 6 meters. I'm using always the units of the International System of Units. So between 10 to the minus 6 and 10 to the minus, at this level, the mayonnaise has the very simple formula, W anti/O. Okay. Now, I don't know why I put this definition of the book, probably mistakes, but because I want to move the potato. And the potato, you see, the S1 means the whole potato, or the big solid. Inside, we have W anti/S2, the starch granules in blue. And again, in between brackets, I gave the reference size, the average size, the size of the picture, let's say. Okay. So indeed, when I look at a picture, be it a macroscopic picture or a microscopic picture or not, I have to tell my audience, okay, I'm using this picture. And then I go into describing it. So I just need to describe what I see, which is very simple. Of course, as for any formalism, you can add a lot of details. There are details. I don't want to discuss this at length because I think it is a mistake to add more detail. We want it to get more simple. we can add the quantities, we can add the scale limits, we can describe kinetic processes. For example, with kinetics, this is three different ways of explaining how to make a mayonnaise. It is mayonnaise in progress, okay? You can make a parameter. I'm sure that it can be useful sometime, but for a first presentation, we should not go into this kind of detail. So I can answer questions later. But what is important probably is to focus on dimensions, because I know, in particular, teaching the students at master level, that sometimes they have difficulties. Because indeed, we mix the faces plus the dimension. And now we arrive to formulas that mix the two, and they mix very naturally. For example, no, I will not take this particular example. I will take the next one. So you see the next one is the macroscopic. So you see again, I'm deciding to describe this picture, macroscopic. I have a D2L, which is the source on top. It's over sigma D3S1, the white ball, over D3S2, the yellow ball, over this S2, over D2L. And then you have the description. For a mayonnaise, or an emulsion, it's a D3W, a three-dimensional continuous face, anti-slash, because you disperse randomly something into it, and it is a D0 oil. Okay. You see? And if you want to have a more rigorous definition of dimension, you will find it in the paper that I publish on suspensions. I say it in a word, an object is of dimension 0 if the size in the three directions of space is lower by more than one order of magnitude to the size of the picture. Okay, and you have the same or the equivalent definition for dimension 1 and dimension 2. Okay, so now it's very simple to take all the pictures that you have seen and to make the formula. I will not go into details now because we have something better to do. We have something better to do, just showing the generality of the formalism. For example, this is a shallot, okay? D3 solid, so the shallot is a solid, and inside you have the water, D0, dispersed randomly, okay? So D3 solid, anti-slash, D0 water. Okay, let's use the same formula, but at macroscopic level. And we get a physical system that is formally equivalent to the previous one, the same formula, and it is an artificial gel. Of course, the size of the cells, let's call them cells, is much bigger. They are alginate pairs that are trapped into a gel, okay? But it is formally the same. So you see, it does not mean that one formula applies to only one object, but it applies to only one kind of object. I have to insist that to say that the operators are describing the topology of the system, not the geometry. Okay? Because be it a cube or a sphere, the physical description should not consider it. It has to consider the material. So now sometimes the formula can be longer, but you have to compare it to the description that you would make with words. With words, you would say, okay, it is a gel with a solid network. Inside the gel, we disperse small cells. Okay, let's use the word cells that are liquid. And this liquid are water. And inside the liquid, we have the random dispersion of the small starch granules we have solid. So you see, it's very long compared to the formula. So I don't come back to this picture because I explained already how to make the formula. I don't come back to chocolate because we explain, I think, well, how to make the formula. D3 continuous solid. It is the fat crystal, the fat crystal network, and this D3O for the oil dispersed into it, but not dispersed randomly as for an emulsion, dispersed randomly making a continuous phase. For the gelatin gel, very simple. And sometimes you can make more, you can describe more complex systems. For example, this is a plant tissue, but it's not in the parenchyma tissue, it's at the border of it. And what we see is one of the channels, in the plant tissue, for example, imagine that you have the root of a carrot, you would have channels that would take the sap, the raw sap from the soil up to the leaves. And then after chemical synthesis of mainly sugar and amino acids, the compounds would go down to the root through other channels. So they are called xylem and phloem. And when you put a sample, for example, this is of onion, probably, onion into methylene blue, and you do the right picture, you can see that the methylene blue colorant has moved by diffusion inside the plant tissue. And then, if we want to describe this picture, what do we have to describe? We have to describe the parenchyma part, but as well to take into account the D1W. So it's very simple to make the description because we have the two, the D0W plus the D1W, and you disperse all this into the D3 solid. For this one is an old invention of mine. Decades ago, I invented the fibre to make artificial meat. It is a reproduction of meat. What is meat? Meat is made of fibers, and inside the fibers, you have, I told you before, a liquid, but you can consider as a gel. The cytoplasm is more a gel than a liquid. I made a simplification before. So let's have fibers full of a gel. Here it is, and the fibers are glued by another gel. Now we need the inclusion operator. That the system itself is very simple to make and can be very good. Now we can distinguish the various gel, and this was the goal that we had before. And here I showed two different gels, but there are many other gels. Now, for invention, the first innovation that I made using this formalism was decades ago. I used dice. I got a formula, and I decided to make it. So the picture here is representing the formula underneath. And I decided to make a dish that I called the Faraday in honor of Michael Faraday. So this is the formula. I mean, it has been made easier, and this was the dish that has been made. It is a Faraday of lobster. Now, how to use it? This formalism. We know now how to make the formula, but is it really useful? Because if it is not useful, we should not use it. So, indeed, it was very useful, for example, for sauces. These are the French chemicals, the French classical sauces. There are 451. I know it's a mess, and nobody in the culinary circles knows all of them. For example, what is a sauce cardinal? What is a sauce groseille? What is a sauce moutarde? What is a sauce Newburgh? What is a sauce Bercy? Sometimes we have the feeling that we know them, but very frequently, I check with chefs that they are wrong, and because it's too difficult. So the question is to organize, and the best way to organize sauces is to organize by considering the physical state. So first, a solution, then an emulsion, then a foam, then a gel, and so on. So I took the 451 sauces, I made them under the microscope, I got the formula, and here were the formula, 23 categories only. So very simple. And indeed, it's a detail. When you compare, for example, a béarnaise or a hollandaise or a custard, they are the same physical system. So probably we should teach the system, not the sauces. The sauces should come later, because imagine that you are making a béarnaise, for example. Béarnaise means shallots and vinegar. You boil it to reduce. Then you add a spoon of water. When it's cold, you add an egg yolk, and then you eat. And when it's becoming viscous, you add some butter, then you emulsify. Should you add pepper and salt? Yes, no, it depends on your taste, which means that the formula, the NDSF formula will not change, but the flavor can change considerably depending on the ingredients that you. So you see, I stick to the idea, the formula are much more important than the recipes themselves. Indeed, using the formalism, I could show that the number of kind of sauces increased since the Renaissance. Okay, and now the main question is there. You have the set of all formulas. From formulas, you can make physical system, and this physical system have chemical and physical properties. Can we predict the physical and chemical properties from the formula? This is a big issue. Until recently, I was saying that I would be dead before someone would find a solution to this big question. It's a big question because it is the same that for drugs. For drugs, the people in pharmaceutical circles have the question of, can we predict the effect on the body of a drug for which we know the chemical formula? So this is the same kind of question. Perhaps I will come back to that later if we have time. Now, what I want to tell you is that using microfluidics, you can easily transform the formula into physical system. For example, this was done with Volker Essel. Volker was in Mainz, now he's in Adelaide. This is a pump in orange, and at the bottom left, we have 3 microreactors, and after 2 or 3 hours, we were able to transform a formula into a food system. This is a food system. Later on, we built a system called the Pianoctel, and there were 6 pumps, a computer driving, and we made cocktails sur mesure at the Frankfurter Fair. And here is the apparatus that I dream to have in my kitchen daily. The core of the system is this microfluidic system. With this system, you can make 500 billion possibilities, which mean different kind of sauces. Okay, now some results, because we want both to describe, to understand, to discover, and to innovate. Okay, with a very simple program, playing with faces, dimensions, and faces, dimensions, and operators, I calculated all the gels that are possible. Okay, so they are here. In this picture, they are gel of class 2, which means that it is dispersed into a solid, finally, but there are 2 faces dispersed into a solid. Now, if you take any of this formula and you read it correctly, you can have an idea of the gel that you will get. Imagine that you have an X with a liquid continuous phase. There will be a diffusion. So you see, the properties can be seen from the formula. Imagine that you have oil or water, and you release, for example, an odorant compound or a taste compound. You will see it on the formula. For example, if you have a continuous phase with water, what you will perceive will be the taste. not the odor. But, except if the odorant compound is soluble into water, which is not so frequent. But imagine now that as for chocolate, you disperse an oil, and then the oil will release odorant compounds, not taste compounds. So you see, from the formula, you can easily have an idea of the system. Okay, so now I'm moving to sources or suspensions. Suspensions are defined to be particles are dispersed, okay? And the same kind of program has been made. So first, for class one are the most simple system. Here they are. So you see, before using the program, I was not able to find them all. Indeed, I did not try hard because it was useless. But now I have it. I just have all the possibilities. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24. Now, if we move to class two, we are certainly not able to predict all them. And here they are, 362. This is only the beginning of the pages. And there are other possibilities for forms, for emulsions, and so on. Now, coming back to properties, I told you about properties very briefly. Now, these are the two release of flavor for two different systems. This flavor release corresponds on the left to a pesto that has been made from, so the two pestos, there are two pestos. They have been made from the same ingredients, the classical ingredients. So pines, Parmesan cheese, basil leaves, garlic, and oil, lemon juice, salt, pepper. On the left, it has been made with a mixer. The color is brilliant green, and then you have wow, immediately the flavor. On the right, it was made with mortar and pestle, and the flavor appeared after some length. Of course, if we mix the two, you have the two properties. Can we make a food with one flavor disappearing, another flavor appearing and disappearing, and so on? And the answer is yes. It has been made. Sorry, it has been made in Denmark after a session of 1 day between PhD chemists and chefs. Okay, this is the DSF formalism. It is described in the Handbook of Molecular Gastronomy, not the NDSF, the new dispersed system. I'm sorry, but for the next edition of the handbook, there will be a correction. And now it's finished because I used 50 minutes and it's time for questions. Thank you. Here it is. I unshare now if I can. How do I unshare? I don't know. How do I unshare? Here it is. Unsharing. It's unshared. Is it unshared?
No, it's still low. We still see your desktop.
Sorry. I don't know how to make save. And now?
No.
Stop sharing. It's the other page. Sorry.
Yep. Good.
Very good. So ready for question if you have.
I have one for the emulsions. Can you hear me?
Yeah.
Did you do one for Ramsden emulsions? Have you a formalism for that?
First of all, I have to congratulate Rogine heavily because she said Ramsden emulsion and not Pickering emulsion. So I'm very happy because generally people speak of Pickering emulsion and they are wrong because Ramsden was 1 year before Pickering. Indeed, if you show me a picture of a Pickering emulsion, of a Ramsden emulsion, sorry, it's very easy to describe it, because imagine that I'm looking at a picture on which I see an oil droplet surrounded by some particles. Indeed, there will be a layer of particles, and the layer of particles is dimension 2 topologic. I mean, imagine that you have this layer. If you open it, you have a flat surface, which means that it is dimension 2. So it is a dimension 0 inside the dimension 2. Or D3, it depends on the reference size that you consider. But there is a surface, and within and inside you have a part. So you see, it's not difficult to describe. We are not considering, if we have to look at the picture. As this picture, we will not be able to see, as the picture that I imagine, that I'm describing now, I will not be able to distinguish the various particles, because they will make a continuous surface. Otherwise, the emulsion will not be very stable. So you see, it's not difficult.
Okay.
Another one?
Yes, I have a question, Herve. I guess the industry, the agro-food, is using a lot all those systems to hide the low quality food and make it for all public to eat more. Do you think they're using all the tips you are sharing to do like bad food into like proper food?
By the way, okay, I have to tell you that very soon I've been asked by a big company to make a seminar for their team, which is not the first time. I will be happy to do it, because it has no relationship with the quality of the food produced. By the way, look at yogurts, for example. The yogurts that I'm making myself are not so good as the one by Danone. So I cannot say that the industrial food is bad quality. In the industry, some people will sell bad quality product, and some other people will sell high quality product. You know, I'm as a scientist, I'm there to publish what I'm producing, and anyone can use it. And this is why I'm publishing it openly, not keeping it for some people of the industry. And indeed, they don't need me, except that they need me and they ask me to help them. And I'm very happy, because, you know, I want the work to be done fairly. Imagine that you have a team, even because what does mean an industry? 10 people make a company, or 2 people, even kitchen lab, make a company. You see, the big issue for me is to be clear about what we say and what we receive. And if I say a cat, it should not be a dog. And if I say an emulsion, it is not a foam. And for example, with people using siphons, many of them have the idea that they're making an emulsion of the foam. They don't know. And many of them say, we make an emulsion. And indeed, when you look at the microscope, they make a foam. Of course, you can make an emulsion with a siphon, but then you should not put gas bubbles, because it is a different story. So what do we say? It's important. And because the food systems are more complicated than simple emulsion or simple foams, we need to go into this kind of description. Otherwise, we have very, very long system words, and the sentence are too long and nobody is. And indeed, it's when you say oleogels, okay, oleogel, what does it mean exactly? When you see at the paper, there were different meanings for oleogels. And today, when I see a paper, I don't know what is an oleogel. It is the same kind of confusion than with fatty acids. There are no fatty acids in oil. There are fatty acid residues in triglycerides. If people are using fatty acids because they are fatty acid residue. When you look at the scientific paper, you don't know if they are measuring the content of fatty acid or the fatty acid residue, which is not clear. And if it is not clear, then bad people can go inside the story and they can cheat, or we have to be clear. We have to be honest and clear. So this is why the formalism, it's not ambiguous. And then it has many advantages for innovation, for description. But the description inside the team, imagine that I tell someone, can you make a jellified foamy suspension? Okay, my team would have to think, okay, a jellified foamy suspension, very complex. But now if I say it is a W anti-slash parenthesis G plus S, it's very simple. I see first that it is water, so I will begin with water, and then I will have to disperse. So for dispersion, I will use a siphon or a whisk or ultrasonic probe. What should I disperse? Okay, some solids, okay, and some gas. So probably the sonicator is not good because for the foam, I would need a pump instead. By the way, I take the advantage of this example to tell you that I'm fighting the siphons today because the siphons are using protoxide nitrogen, which is used for addiction. And I insist that people should use pumps, compressors with small dispersers like you have in your garden. And in the garden disperser, you put an emulsion or the liquid of your emulsion, you have the compressor, you have it, and you have no renewable cartridges, which cost a lot. So this is a call for all my friends in the kitchen: drop the siphons. Another question? Was it clear enough? Yeah, very good. Okay. So no question. Very good. So I have to stop the recording. I will put that online. And if you want to come to Colmar soon in May, don't forget to apply and to send abstract. So, okay.